So it's a pleasure to introduce the talk of Hanspeter Kraft from Basel, Switzerland. He's going to talk about smooth G-varieties. So please go ahead.
Okay, thank you very much for this invitation to this interesting seminar. I checked out these many really funny titles and interesting titles, so it must be quite a good seminar. So this is, as said, joint work with Andriy, Regeta and Susanna Zimmermann. Both have been former students of mine. Susanna is now maîtresse de conférence in Angers. Andriy is still postdoc and looking for a job somewhere. So now I should, let's fix, I should say the starting point was in fact the diploma work of Susanna, and it was quite a different subject. I was wondering what we could say about, let's say, the invariant theory, representation theory, classical invariant theory of the affine group, not GLN, but of the affine group. So essentially nothing is known. And doing this, we discovered some interesting features which didn't have anything to do with the affine group. And this is now what came up, this small G variety. So I use the standard notations, be working over the complex numbers. We could take any algebraically closed field of characteristic 0. G will always be a semi-simple algebraic group, maybe even a simple one. B is a Borel. I once heard a talk of Armand Borel, and he said, let B be a me. So T, a maximal torus. In B, U, as usual, the maximal unipotent subgroup. And I fix lambda G, the monoid of dominant weights, as usual. The algebraic quotient X here is an affine G variety. So we are, really the important part is we are sitting in affine varieties. The whole projective situation question of the same has not been worked out yet, or the general one. So the algebraic quotient is simply the map given by the invariant ring. So this has these basic properties like it's always surjective, every fiber contains a uniclosed orbit, and it carries the quotient topology. And even it carries the quotient topology also as a C variety. Standard from the notation for GLN, we have the upper triangular matrices, we have the diagonal matrices, T, the torus, we have the upper triangular unipotent matrices, and here the dominant weights are exactly the span of the omega I, and omega I is the fundamental weight of wedge I, so of the exterior, of the ith exterior power. Now, what is a small G variety? One thing could be small dimension. That's the first thing you think about. You will see this is quite the interesting part. If you usually, when you look at these things, you start with the smallest group. And this is, of course, here SL2. However, SL2 is just a case where nothing works. So it's the first time in my career where SL2, SL3, SL4, and even SL5 are essentially not interesting. It's going to be interesting only for higher n. You will see. This is quite one of the invention we made. Now it could also be a small invariant field being small. You know that if this invariant field is just the constant, this is equivalent that G has a dense orbit in X. That would be a small invariant field. Or small complexity. The complexity is measured by taking the field of invariance under the Borel subgroup. And for example, if the Borel has no invariance, so small complexity 0, this means that this orbit is a so-called spherical orbit. Let me give an example. I start with SL2, as everybody should do at the beginning. If we take dimension 2 and smooth, remember we are acting on affine variety. There are two examples, SL2 mod the torus and SL2 mod the normalizer of the torus and the standard representation. These are all smooth dimensional 2 SL2 varieties. If we only assume normal, then we have in addition the quotients C2 modulo the finite cyclic group of order k acting on C2. So this, as soon as k is larger than 1, this is not anymore smooth, but has an isolated, the famous k-type singularity in the origin. If we go to dimension 2 in general, then in fact, the classification corresponds to the rational curves with a non-trivial fixed-pointed C-star action. This is one of the outcome of our theory here. So the rational curves with non-trivial fixed-pointed C-star action, this is the same as dimension 2, general dimension 2 varieties under SL2. Now let's take the next case, 3. I believe that classification here is possible. One case is, of course, the case of a dense orbit. The affine variety with a dense orbit with trivial stabilizer, they have been classified by Popov long ago. And this has led to the whole embedding theory. This was the starting point of the whole embedding theory of groups embedded or homogeneous spaces embedded in varieties. But what has not been done here yet is the dimension 3 case, which has not a dense orbit. So essentially, because it's affine, the orbits are then two-dimensional or fixed points, and the classification of those is not completely trivial, but I believe it could be done. Dimension 3, larger than 3, I would say it's completely hopeless. I wouldn't have no idea how to classify 4-dimensional SL2 varieties. So this seems to be a difficult point. So that's SL2, and usually called the easiest case. Interestingly, if we make a large n, as mentioned before, the situation improves. Here is a rather amazing result. Assume n is greater or equal 5, so we are at least with SLn, SL5. Then every smooth affine SLn variety of dimension less than 2n is an SLn-vector bundle over the quotient. So this is, so for an SL5 variety of dimension 9 is automatically, smooth one is automatically a vector bundle, and the quotient is also smooth, and the 5s are either the standard representation or the dual. And a similar result we have for SP2N, but it's definitely not true for SL2, not true for SL3, and not true for SL4. So that was in some way a surprise for us. What's the reason for that? Yeah, the reason is the following. If n is greater or equal 5, then an affine SLn variety whose dimension is less than 2n contains only so-called minimal orbits. And the minimal orbit, I have to discuss this later, is essentially an orbit of a highest weight vector. Minimal orbit and fixed points are nothing else. That's the only object which appear here. And again, this is wrong for SL2, SL3, and SL4. But starting with SL5, this is true. So let's discuss these highest weight orbits. This is also quite an old story. It goes back to work of Popov and Weinberg long ago. So let me denote by V index lambda a simple G module of highest weight lambda. Then the highest weight orbit I will denote by O lambda. So you take a highest weight and take its G orbit. They have been studied, as said, 1972 in an interesting paper by Weinberg and Popov. First of all, what they showed is if you take the closure, then it's always normal. It's always normal, and the only additional point is the origin. So you add to the orbit the origin, the closure is normal, and the closure is also cone, so it's stable on the scalar multiplication. Second thing, if you take any k and you take the highest weight orbit corresponding to lambda, and that one corresponding to k lambda, there is a canonical cyclic covering of degree k, from lambda to k, OK lambda. This cyclic covering extends to the closure, and defines a finite morphism of degree k. Moreover, the automorphism group, the G equivalent automorphisms, are only the scalar multiplication. Now, this is true for O lambda and for its closure. Now, what about the dimension of these orbits? You remember, I will call them minimal, because in some sense they are the smallest orbit, and this can be made precise by the following lemma. Oops. Yep. Take any G module, or any variety, but G module is better. Take any non-trivial orbit, O in this G module, and consider a connection, a projection onto an irreducible representation, G-linear projection, with the condition that the orbit is not in the kernel, so the orbit is not sent to the origin. Then, in fact, the dimension of this orbit is greater or equal to the dimension of the minimal orbit in V lambda. So you see, when you have any G module, the smallest possible dimension of orbits in there is always attained by a minimal orbit. However, one has to be careful. It could be that the smallest dimension, an orbit of smallest dimension, is not a minimal orbit. So this is a delicate point which we have to discuss later. So I said I use the following notation. I say any G orbit isomorphic to a highest weight orbit O lambda is called a minimal orbit. So the minimal orbit, I mean, the name is now somewhat justified by the previous lemma. They are minimal in a certain sense. I also need the kind of type. You remember the O lambdas and the OK lambdas, they are covering from each other. So O lambda covers OK lambda, etc. And I call the type of this orbit the smallest lambda knot in this line. So you can easily see if you take any highest weight lambda and you take the intersection of Q of the rational multiples with the dominant weights, it's exactly the integer multiples of this lambda knot. So the lambda knot is the shortest one. This one I call the type of this minimal orbit. Here is the first proposition. Let X be an affine G-variety or any orbit, then the point is O is minimal if and only if the closure minus the orbit is a single point. So remember, we know that for minimal orbits, but this is a characterization of minimal orbits. This holds in every variety. Secondly, every non-trivial image of a minimal orbit under a G-equivalent morphism is again a minimal orbit, and this one has the same type, does not change the type. Thirdly, a finite connected covering of a minimal orbit is also a minimal orbit, and it's also of the same type, and this covering is automatically cyclic. And finally, if the closure of a minimal orbit is smooth, so if this additional point which comes in is not a singular point, then this closure is automatically a simple G module. Typical cases take the standard representation of SLn. This has a dense orbit, and the closure is the object itself. This is somewhat the geometric characterization of minimal orbits. So one has just to keep in mind, you take the closure and you exactly at one additional point, then it's minimal. Now, what about the algebraic characterization? It's the following. Let me first define the concept of a G-algebra. A G-algebra is a C algebra with a locally finite and rational action of G by algebra automorphism. So the typical examples, and the only one we are going to use, are the coordinate rings of affine G-varieties. So the action is locally finite and is rational. That's a G-algebra. Then such a G-algebra has an isotypic decomposition. So you decompose it according to the simple modules occurring in this algebra. And then it's a well-known fact from representation theory. If you take the isotypic component R lambda corresponding to the highest weight lambda and R mu corresponding to the highest weight mu, and you multiply them, then you end up in a direct sum of isotypic components, and those appearing are those smaller than lambda plus mu, where the small is the standard partial ordering on the weights. Remember, this is given by lambda is smaller than mu if the difference is a sum of positive weights, a sum of positive roots. That's the ordering you get. So you see, you might, if you multiply the two, you might find R lambda plus mu, but you also might find smaller ones. This is a well-known fact from representation theory. Now, I define, say, this G-algebra is graded if the product is contained in R lambda plus mu. So if you have no, what Luna and Wüst called spontaneous degeneration. So no additional thing, you always end up in lambda plus mu. Then I call it a graded G-algebra. So we assume that there's no isotypic elements anymore which are smaller than lambda plus mu. Here's an example. It's just the important one. If you take a minimal orbit and the coordinate ring from in and its closure, this is the direct sum of the irreducible representation with highest weight multiples of k lambda, the dual ones. And this is obviously, or is easy to see, is a graded G-algebra. It only contains the highest weight module V lambda and those of multiples. So it's just the direct sum of those. This is also, of course, in Popov-Wienberg's paper. Recall the concept of a horospherical variety. Horospherical, we call X horospherical if every stabilizer contains a maximal unipotent subgroup. Horospherical. Usually the one talks about horospherical orbits, but let me give this name for any affine variety. Interestingly, again, here, if you take the U invariant ring, maximal unipotent, then this is a horospherical variety. In fact, the coordinate ring OG mod U contains exactly every irreducible representation of G once. That's one of this famous property of the U invariant ring. U invariant ring also, it contains every V lambda with multiplicity 1. And it's horospherical. So if you multiply two of them, you get, if you multiply in this ring here, OGU, you multiply V lambda with U mu, you get exactly V lambda plus mu. So theorem, an affine G variety is horospherical if and only if the coordinate ring X is a graded G-algebra. So this is in somewhat the almost geometric interpretation of the fact that the coordinate ring is a graded G-algebra. So the effect is every stabilizer contains a maximal unipotent subgroup, or you can say all orbits showing up in the variety X are in fact spherical, horospherical orbits. So that's not really difficult to prove, and I think this is essentially known. Recall, we have the Borel, we have the maximal torus, and we have the unipotent, maximal unipotent. The interesting thing, we can describe the structure of these varieties, which correspond to a graded G algebra. Let me recall some classical stuff. It's not so well, everybody knows what the fixed point is, but the dual concept, the Larsen quotient with a trivial action, is not so well known in general. It's very useful to use it here. So I denote, if I have any H module, H any group, I denote by pi the largest quotient module where the group H acts trivially. Point is, if R is a graded G algebra, and I form this quotient with respect to the maximal unipotent subgroup, then this is in fact, the kernel is an ideal. So the definition is just by module. So a priori, RU is a module, and the map R is a module homomorphism, but a G module homomorphism. But in this case, the kernel is in fact an ideal. And here is the main theorem. It looks a little strange, so we have just to look at it. I start with a graded G algebra. Then the interesting point is there is a canonical G equivalent isomorphism, which is of the following form. You take the coordinate ring of G mod U. Remember, this is exactly this algebra which contained every irreducible representation once. You tensor it with the quotient RU. Then, of course, you have on both modules, you have an action of the torus, because the torus is normalizing U. And then you take the fixed point under this torus. And the point is, this what you get this way is again your algebra R. In addition, if you look at this quotient R index U, this quotient induces an isomorphism if you take the fixed point under U minus, so the opposite unipotent with RU. So what does this object, what does this theorem tell you? It tells you that the algebra R is completely determined by the fixed points under U or by the quotient R mod RU. So you only need to know the U fixed points in order to reconstruct R. This is the content of this theorem. So this means we can reconstruct R from its U invariant, because I mean the U invariants and the U minus invariants are essentially the same. They determine the quotient RU, and you get this isomorphism here. So that's the algebra, algebraic property, structure property of a graded algebra. Now we should apply it to the geometric setting. So recall again, minimal orbit is an orbit of a highest weight vector. I already mentioned before that for a minimal orbit, the coordinate ring O lambda is a graded G-algebra. Theorem. Start with an irreducible affine G-variety. Assume that all non-trivial orbits in X are minimal. Then, in fact, OX is a graded G-algebra, and all minimal orbits have the same type. So here you see we have exactly what we were looking for. The geometric assumption is it only contains minimal orbits or fixed points. And the algebraic consequence is then it's automatically a graded G-algebra. So this is now the definition, my definition of small. I call an affine irreducible G-variety small if the non-trivial orbits are all minimal orbits. Main theorem. Here's now the geometric picture. We start with a small irreducible G-variety. Then the first remark is the G-axiom is fixed pointed and all minimal orbits have the same type lambda naught. In particular, that's a consequence of fixed pointed action. The fixed points under G are mapped isomorphically to the quotient. And recall fixed pointed means every closed orbit is a fixed point. There are no other closed orbits. And X to X mod G is as usual the algebraic quotient. So small G variety, this is one remark. Secondly, there is a canonical C star action on XU. It has to be defined in a good way. It's not necessarily faithful, it's a canonical C star action. This C star action on XU is also fixed pointed, and the quotient of XU modulo C star is the same as the quotient of X mod G. Recall the automorphism group of O mean is C star. And now the claim is here, the structure. You can reconstruct your variety X from the U fixed points using this C star action on XU and on O lambda naught bar. Remember, O lambda naught was the type. So O lambda naught bar is a normal variety, the closure of this minimal orbit. And it's a C star variety. And we have a canonical action C star on XU. And this is the reconstruction theorem. So XU completely determines X. Finally, X, the fixed point under XU, is the same as the quotient by u. In particular, this variety X is normal if and only if the fixed points are normal, if and only the quotient is normal. So the normality can also be read off from XU. Corollary, fix a type, call it lambda naught. Then the functor which sends X to the XU fixed points defines the equivalence of categories. On one side, the irreducible small G-varieties of type lambda naught, and on the other side, the irreducible affine positively fixed pointed C-star varieties. The positively fixed point is the following. Fixed pointed means the only fixed points at the only closed orbit are fixed point, whereas positively fixed point means the limit t to 0 tx always exists. In general, we would only know the limits either t going to 0 of tx or either t going to infinity. But positively fixed point, it means this limit always exists. And the inverse functor is the one I did describe before. To y, you associate this product here, this associated product. You've formed a quotient of O lambda naught, the product of O lambda log y, and you divide it out by the action of C star. So this is now an equivalent of these two categories. You see also normal x corresponds to normal xu on both sides. And here is, let me just start with one quite interesting example. I start from the C star action. So I take C3 and the C star action with the three weights 2, 1, and 0. So on the first coordinate, it acts with t squared, on the second with t, and on the third coordinate, it does not act at all. Here, the variety x times z minus y squared, this is an invariant, a C star invariant normal surface with an isolated singularity in 0. Yeah, it's clear. It's a surface. It's normal because x, yes, this is known, and it's invariant because x times z has weight 2 like y squared. The quotient by C star is just a projection on the last coordinate. It's also easy to see. And the interesting thing is, if you look at the fibers of this quotient, then you see all the reduced fibers are C. But reduced, there is a fiber which is not reduced, because you might remember if you have a morphism to C, where all the fibers are C, the schematic fibers are also C, then in fact it's a principal bundle. This is not the principal bundle, and the reason is there is one fiber which is not reduced, but you don't see it. You just, as if you look at the fiber, they are all C. But if we make now the corresponding construction, so I take the C representation, the interesting point is the C star representation on these fibers is faithful if A is not 0, but it has the kernel plus minus 1 for A equals 0. For this non-reduced fiber, the C star action is not the same than on the other ones. And if we are going now to define the corresponding SLn-varieties, I take this interesting surface C star, I take Cn, which is the closure of a minimal orbit, and then it has the following result. For the reduced fibers here, now we have the inverse image is a standard representation as long as A is non-zero. This corresponds to the above, where the fiber for Z is reduced. But now you see a huge difference between the 0 fiber. The 0 fiber now became the closure of the minimal orbit of weight 2 omega 1, which is Cn modulo plus minus 1. So you see, if in the original S, you couldn't see the difference between the fibers. If you make this construction, you immediately get a difference. And the reason is that the C star action is not the same on these fibers. Okay. Next one. Let me give here another example. Okay. I take let me say where this example goes back. We know, it's known that you can embed every smooth affine variety of dimension d. You can always embed in an affine space of dimension 2d minus 1. So if you have the dimension and it's smooth, if you have singularities, there's also a statement. So it was a question once, I think I asked the question to a student, is it true that we have a similar statement for equivariant maps? So let's say we have SLn-variety of dimension d. Can we always embed it in something, in a module, an SLn module, whose dimension is, let me say, 5 times d, or the d square or something like that? So the same question was, can you somewhat, if you know the dimension of your G-variety, can you estimate the dimension you need to embed this into a representation? That was the question. Now here is the following example. Let n1, n2, and s be positive integers. Then there exists an affine SLn variety x of dimension n plus 1 with the following properties. First of all, the quotient is C, the line. You got dimension n plus 1, and so it's 1 less. Secondly, there is a finite subset y1, ys. You see the same number as the positive integers with the following property. If you remove this subset, then this quotient is a trivial bundle, y z minus f times cn with fiber cn. However, the fibers over these special points are cn modulo mu ni with the given ni above. So the previous example was just the case of a single, of n1 be a single one. This is, you can do it with any number of positive integers. Now, what's the consequence? If we choose the numbers ne all different, then the equivariant embedding dimension of x is summation ni plus 1. So you see, x has dimension n plus 1. There is no way embedding dimension means the smallest module you could embed it into it is given by summation ni plus 1. So there's no way to give an upper bound which only depends on the dimension x. And the fact that this embedding dimension is at least this is because the ni omega 1 only lives in this module. It cannot live in a smaller one. So this solves the embedding problem, the equivariant embedding problem, in a negative way. An SLn representation containing x as a closed SLn stable subset has dimension at least summation ni plus 1. So it can be made as large as you want. Theorem? Oh, okay. So this is the second example which indirectly uses the construction before. I didn't say anything about smoothness. Let me give here the theorem. X is again a normal small G variety of type lambda naught. Then the following statements are equivalent. The quotient is a smooth morphism. Secondly, the quotient is a G vector bundle with fiber V lambda naught. And thirdly, the quotient of the fixed points X, you remove from the U fixed point the G fixed point, and you map it onto X U mod C star. This is a principal C star bundle. And V lambda naught is the closure of this minimal orbit. Finally, if X itself is smooth, then the above assertion are all satisfied. So you see the smoothness for a normal one. I couldn't remove normal, so I need normal a priori. Quotient smooth, quotient being a vector bundle, and the quotient with respect to U is a principal bundle, are all the same statements. And a smooth one satisfies this. So for example, one consequence is if X is smooth, then the closure of this fourth minimal orbit O lambda nu must be a representation. So corollary, there are no smooth small G variety for simple groups different from SLn and SPn, SP2n. And the reason is only SLn and SP2n admits an irreducible representation which contains a dense minimal orbit. For all other simple group, it's not the case. And for SLn, it's a standard representation or it's dual, and for SPn, it's a standard representation. If you think about the orthogonal group, then you always have an invariant, so there cannot be a dense minimal orbit. And you can argue for all other simple groups in the same way. Now, if you want to make any application, we need to compute some dimensions. And this was quite a lot of work. So let me introduce the following object. Mg is the minimal dimension of a minimal orbit. So not all minimal orbit have the same dimension. So this is the minimal dimension of a minimal orbit. Dg is the minimal dimension of a non-minimal orbit. So the other ones, quasi-affine, of course, because we are only interested in orbits showing up in affine varieties. And finally, they are always around the reductive, the closed orbits. And you might remember a closed orbit is always of the form G modulo reductive group. So we also need Rg, the codimension of reductive subgroup, so the minimal again. So these are more or less the minimal dimension of an orbit of the form G mod H, where H is a reductive subgroup. So this is the minimal dimension of a closed orbit. So Mg, Dg, Rg. Now, what do we know? First of all, as we already know, the Rg is already greater or smaller dg by definition, and dg is always greater or equal mg. So that's obvious. The interesting thing, but is if dg, so if the next possible non-minimal orbit has dimension strictly larger than mg, or dg greater mg, then it follows that every irreducible G variety of dimension less than dg is small. Because there is, if less than dg, there are only minimal orbits left, all others are gone. So this is the interesting point. We have to find out if dg is definitely larger than mg. Here is the table. And you check it. A1, mg is dg. A2, mg is 3, dg is 4. Also not interesting because only dg is smaller. Same for A3, 4, 5. And now an for n large enough, it becomes 2n and n plus 1. So there's a lot of space in between. B2 we have 4 and 4. Bn, we have 2 and 2n. Cn is again interesting because one side is the dg is 4n minus 4, whereas the mg is 2n. Dn, both numbers are the same. E6 here comes 26 for dg, 17 for mg. E7 again, a gap, 45, 28. E8, 86, 48. F4, 16, 16, G2, 6, 6. So you see the only interesting cases where the mg is definitely smaller than dg is the type an, the type cn, and interesting, the e6, e7, and e8. All the rest is not interesting. G2 not, F4 not, Dn not. So, only interesting case is an for n greater 3, cn for n greater 2, and e6, e7, e8. So, as an example, if you have an e6 variety of dimension less than 26, it's automatically small, and is completely determined by its u fixed point, etc., etc. So here is the example. D E6 is 26, D for E7 is 45, and for E8 is 86. And thus the E6 varieties of dimension less than 26 are small. And there are a lot. There are many. Now, what about smoothness? Let G be a simple group of type E. Every affine G variety of dimension less than dg is singular. No smooth E type of smaller dimension. There are many non-closed orbit of this dimension. I mean, an orbit is always smooth, but we are thinking about affine. And these orbits do not show up in dimension less than dg. They are not closed. Whenever you close it, you get singular points. So there's no way to find anything smooth. So we have mentioned that the Horospherical case means all stabilizers contain a maximal unipotent subgroup. This is equivalent being graded. Now there's an interesting question. Do we have some kind of a better geometric characterization of Horospherical G-varieties? I mean, the statement saying that all orbits are horospherical or every stabilizer contains a maximal unipotent is not such an interesting fixed point. And once we would have it, it would be quite interesting to see whether we find examples of horospherical varieties which have larger dimension as the one we have already found with the small varieties. And then for the horospherical, we have a similar statement about the classification. They are completely classified by the U fixed points, and the whole theorem applies. Okay, that's what I wanted to throw. Thank you very much for your attention.
Okay, so thank you for the talk. So questions, comments, so you can use the chat. I recall that. Who is first?
Hanspeter, you mentioned that there may be a similar theory for projective varieties. Can you say a little bit about that?
I think I mentioned what I said is the similar theory for projective varieties is not done yet. So at this point, so there are completely different phenomena showing up. So the similar, by a similar, I would mean, is it possible to say that if the dimension is small enough or has a certain property, then we can somewhat completely classify them. This was the upshot here. The upshot was that a small variety, the classification is given by C star actions. So, and the people somewhat believe with the C star varieties, we have all the tools from combinatorics, etc. We understand them like toroidal embedding much better than we understand, for example, spherical embeddings. So that would be, but at the moment, I have no idea what that could be.
Okay, other questions? No.
No questions.
No, I mean, it was so clear.
That's always the two possibilities. Either it was clear, or it was completely ununderstandable.
No. Okay, so maybe this is because it's beginning of this new session, so people are afraid of the Zoom. Bon, mais okay, so of course you can contact independent